This is section 6.2. We're talking about part 2. In part 1 we talked about multiplying radical expressions. Part 2 we're going to talk about dividing radical expressions, and then we're also going to add in rationalizing the denominator. Because remember, again, when you'll find this out, you've had this before, you can't have a square root in the fraction, bottom of a fraction. Okay, so since you divide division in terms of multiplication, okay, we can extend the property for multiplying radical expressions. Okay, if indexes are the same, you can write a quotient of roots as a root of a quotient. For example, same thing we do with multiplication. If we have the square root of 2 times the square root of 3, that's the square root of 2 times 3. Okay, well, it's the same thing for division. If I have the square root of 2 divided by the square root of 3, this is essentially the square root of the whole thing, 2/3, 2 divided by 3. It's the same thing for other roots as well. If I have the cube root of 4 divided by the cube root of 5, then I could say this is the cube root since they're both the same index. Now, if they weren't the same index, I couldn't do this. Okay, but since they're the same index, we can do that, and we can say that that's the cube root of 4/5. Now, division, okay, again, same thing here on division. What we're going to try and do is we're going to try and see if we can make the same root over the whole thing, simplify as much as we possibly can the radical expression. Okay, so let's take a look at some examples. All right, first example, letter A here. Okay, we've got the square root of 18x to the 5th over the square root of 2x to the 3rd. Since they're both the same root, what I'm going to do is I'm going to put them underneath the same root. So 18x to the 5th divided by 2x to the 3rd. Okay, now we can go ahead and simplify since they're all in the same root now. 18 divided by 2 is 9. Okay, and your exponent rules, remember with your exponent rules, what we do with division, we subtract. I take large minus small. So I take 5, in this case I take 5 minus 3, that's 2, and where's it left? It's left on the top, which means I don't have a fraction in here anymore. So this is just the square root of 9x squared. Well, this is just what we did before. Okay, we did on Friday and on Thursday. The square root of 9 is 3. The squared term of the x cancels out with the square term of the index, and all I'm left with is an x, and this is my answer. Okay, so let's take a look at the second example. Again, these are both the same root, so I'm going to go ahead and put them under 1. 162y to the 5th over 3y squared. Okay, now 162 divided by 3, since they're both under the same root, I can simplify this. 162 divided by 3 is 54. And I have 5 y's on top. Take away the 2 y's that are on the bottom, and I only have 3 left on the top. So I no longer have a fraction. Okay, now I've got to break down the number 54. 54 breaks down to 9 and 6. This is 3 and 3, and this is 3 and 2. So I've essentially got 3 cubed times 2. So I'm going to replace that. Again, this is what we did on Friday and on Thursday. So this is 3 cubed times 2 times y cubed. My cubes and my cube root will cancel. The index will cancel with those. So my 3 goes on the outside. My y goes on the outside. But my 2 is going to stay on the inside because I can't take the cube root of 2. And this is my answer. Okay? So it's not horribly different from multiplication. In these cases, these problems were nice because the fractions went away with simplifying. Now, what happens when your fraction doesn't go away? Because that's going to happen. You're not going to have every single problem be where it's going to simplify for you. So we're going to have to simplify a radical expression by rationalizing the denominator. Okay? And what they've done here is they've given you an example. Remember, this is stuff from the past. If you have 1 over the square root of 2, you cannot have a square root in the denominator of a fraction. So in order to get rid of that, we multiply by the square root of 2 over the square root of 2. Okay, and then we simplify it, and you'll notice we don't have a square root in the denominator anymore. Okay, So you're going to do the same kind of concept here as you would with just a regular square root. So let's take a look at this example. We have 7x, the cube root of 7x over the cube root of 5y squared. Well, you'll notice that neither one of these will come out of this root because they don't have enough. There's not enough of a third power. So I've got to get rid of this denominator. So what I'm going to do is I'm going to multiply top and bottom by the cube root of 5y squared. So now we're going to tie in multiplication with the division as well. And what that's going to do is, on the top, what I'm going to do, since they're cube roots, I'm going to combine these. So this is the cube root of 7 times 5 is 35. X is there and a y squared is there. On the bottom, when we take the cube root of 5y squared times the cube root of 5y squared, the cube roots are going to cancel each other out, and what's left? The only thing that's left is 5 and y squared. Okay, now, the only thing that breaks down 35 is 7 and 5. Those are both prime numbers, so I can't, there's no cubes that will go in there. And these other variables are not going to be able to be taken out. Now, the one thing that's going to catch some of you that you're going to try and do is you're going to try and cancel this y squared with this y squared, but you can't do that. Okay, again, remember, the square root is like jail. Nobody comes in, nobody gets out unless you have specific qualifications. Okay? So, this is your final answer right here in this case. Okay? All right, let's take a look at the last example here now. We've got 12y squared z on the bottom, and again, it will not cancel out. Nothing will get out of that with that third root. So I'm going to multiply by the cube root of 12y squared z over the cube root of 12y squared z. Okay? When I do that, on the top, again, since they're both cube roots, I can combine things. 12 and 5 is 60. Now, you'll notice 5 is prime. 12 breaks down into 2 squared times 3. And you'll notice that none of those numbers, those base numbers, have an exponent of 3. So I can't break down 5 and 12 anymore with a cube root. I've got an x squared, I've got a y squared, and I have a z. On the bottom, the cube roots are just going to cancel, and I'm left with a 12y squared z. Okay? Now, as you look at this, again, these variables, none of these variables are going to be able to come out because they don't have at least 3, and there's no third power that goes into 60. Okay? Down here, remember the y squareds cannot cancel because this is in a root, this is not. Okay? So in this case, you are done, and this is your final answer. So that kind of gives you an idea of how to rationalize the denominator a little bit. Now they're going to combine these, use simplifying a division with rationalizing a denominator as well. So they're not always going to be like the problems were before on the previous page where they all divided out nice and evenly for you. Okay? All right, this concludes section 6.2, part 2 of division of radical expressions. Okay? Don't forget to complete your WSQ once you get done watching this and answer those questions.